Okay, so in the last lecture, we talked about the notion of the separation between locations. Now, the separation between locations, in a way, depends on the shape of the surface that you are required to walk around on. If I'm walking around on a flat sheet, I could say the separation between nearby locations is just going to look something like the Pythagorean theorem. But if I'm walking around on a curved surface like a sphere or a donut, then the separation between locations can look more interesting from a mathematical standpoint. Now, in this discussion, I am assuming that I'm required to travel on the surface. So if I want to travel from Madrid to Cape Town, I'm assuming I must walk along the surface of the earth. I'm not allowed to dig from Madrid to Cape Town or anything like that. So now, up to this point, we considered the separation between locations in space, but we also could extend this idea to consider the separation between locations in time and separations between locations in space and time. So I am going to define an event as being a very specific location in both space and time. So for example, an event could be my astronomy lecture recording studio, which is right now just an empty dining room, and this is my location in space. And the location and time that this is occurring is about 5:30 on Thursday. So here's my location and time. The combination of my location in space and time is my location in space-time. And all of the locations in space and time together are referred to as space-time. So if we want, we could talk about the separation between events in space-time, separation between different locations in space and time. So as a first example, let's consider we have a billiard table. We'll have a camera overhead above that billiard table, and that camera is going to take pictures in very rapid succession. So that camera will take pictures of where the billiard balls are every 1/100th of a second. So here's my billiard table. I'm going to put some balls on the table and have a camera overhead. And I'm going to basically investigate what would it look like if I take a whole lot of pictures of the locations of the balls for different scenarios, where the balls are stationary, where they're moving around. What would that all of those pictures together look like? So as a first simple example, let's consider the red ball is on the table and just stationary. Now for this discussion, I am going to assume we print the pictures on clear paper, so we could always see the location of the ball as time moves on. So if I have a red ball on the table and it is not moving around, I will have just many pictures of the red ball in the same location. As I stack those pictures in succession, I will just see a vertical red line because the ball never changes its position in the photograph. Now, next we could ask, what would we see if we have a ball on the table that is moving? How would that change what this stack of pictures look like? So let's give the blue ball on the table a push. So now it's going to be moving along the table. And if I take many pictures of the blue ball as it rolls along the table, it's going to be starting over here and moving to the right. Originally, the ball was here, but then as time moved on, the ball moved to the right along the table. So I would see now a diagonal line representing the motion of the ball. The very first picture at the bottom of the stack, the ball was here on the table. But at the very last picture, at the top of the stack, the blue ball was roughly here on the table. Now we could ask, what if we have two balls on the table and they're racing? So let's consider the blue ball and the red ball are both moving in the same direction, but we're going to say the blue ball is moving faster than the red ball. If I were to take pictures while this is going on and I stack all those pictures on top of each other, I will see the blue ball has a diagonal line to represent its motion. The red ball has a diagonal line to represent its motion. And you could convince yourself that whichever ball is moving faster will have a line that is closer to horizontal, because every 1/100th of a second, it will move a little bit further than the other one because it is moving faster. Now, based on the way these pictures are stacked, I could also convince myself that the blue ball started out behind the red ball, but it was moving faster than the red ball and eventually overtook the red ball and ended up in front of the red ball. So this picture right here below is the moment at some point when the blue ball is now in front of the red ball. So it'd be somewhere up here, one of these pictures. We could also represent a change of direction in these figures we are building. So in this example, we'll consider the blue ball and the purple are going to approach each other from opposite directions. They're going to collide and bounce back. So the blue ball is originally moving to the right, the purple ball is originally moving to the left. As I take many pictures, originally the purple ball and the blue ball are far apart from each other, but then they get closer and closer and closer as time moves on. They collide right here, and then they bounce back and they're moving farther and farther away from each other. So this picture here, where the balls are approaching each other, would be somewhere around here, give or take. Now, notice that in all of these thought experiments we conducted, we stacked the pictures sequentially. So the bottom picture on the bottom of the stack is always at the earliest time, and the picture on the top of the stack is always at the latest time. So in a way, I could think of this diagram I created as displaying two spatial directions. Basically, these all will lie horizontally when the same in the photograph, and these describe the location of the balls at a very specific moment in time. And because I'm stacking these pictures in order, the vertical direction describes as time moves forward, as time moves on. So I have two directions describing a spatial location, and I have one direction, upward in this case, describing what moment in time it is. Or I could think of that as a location in time. Now, if we want, we could also apply the same reasoning to the path the Earth takes around the sun. So the Earth is orbiting the sun, and with every orbit the Earth makes around the sun, the Earth will travel about 584 million miles in distance, and the Earth will travel, quote unquote, 1 year through time. So if I were to draw the path that the Earth takes as it orbits the sun in a similar manner where I also allow time to be a thing, I would see this helical motion as the Earth is going around the sun, but we're also allowing time to move forward. So this is more or less one very good way to think about how we want to describe locations in space and time. And if we want, we could think about the separation between specific events in space and time. Now remember, an event is a specific location in space and a specific moment in time together. So if you have been paying attention to my hat at any point throughout the modules, you'll know that I am a native Clevelander, and my favorite football team has experienced a certain degree of futility in the last few decades. And so there was a day, Christmas Eve 2016, when the Browns won a game, and so they ended up that was their only win that year. And then there was a season after that, and then there was a season after that when the Browns again won. And if we want, we could say here was a specific event, a location in space and time, when the Browns beat the Chargers. And here's a specific event, a location in space and time, when the Browns beat the Jets. So what is the separation between these locations in space and time where the Browns, let's say, went without winning? And the path the Earth took around the sun between those two events is going to look something like this. So the Earth traveled about 1,022,000,000 miles through space and about 1 3/4 years in time between these two events. So if I want to write what is the separation between events in space-time, I will write the separation between events in space-time to look something like this, where ds squared is negative dt squared plus dx squared plus dy squared plus dz squared. So what I am writing here is, it is required to have separations in space be positive numbers, separations in time squared must be negative numbers. This is required to preserve causality. Now, this separation between events in space and time looks very similar to what we saw for the 3D Python. Oh, no. Go away. So, this separation between locations in space and time looks very similar to what we saw for the Pythagorean theorem in 3D, where we were talking about the separation between locations in space as dx squared plus dy squared plus dz squared, but we're also just adding a negative dt squared to talk about the separation between locations in time. So we have a small increment of time over here and a small increment of space over there. And this negative sign is going to be very important. So what I'm going to do is I'm going to end this now, and I will come with one more video to talk about the importance of this negative sign in the next video.